Okay, so, we have a circle. So I put a set of coordinate axes on it. I wasn't sure what I was going to do with it. There are two possible things, and I decided, well, yeah, we're going to do 12-hour clock, okay? And what do we do with the 12-hour clock? There are two things we can do with the 12-hour clock. So I made a decision, well, let's do this first, okay? But there's a whole new set of functions, basic functions that you get from circles, okay? And we're going to talk about those too. So, but right now we're going to talk about questions like this. And these questions, just kind of spontaneously from answers you gave, lead me to the whole subject of algorithms, okay? Simple algorithm for solving these questions. There are a number of algorithms that we can use to solve this problem. Now, an algorithm, well, there's one algorithm that you learn young. Okay, long division is an algorithm. You take this and you divide it into this, see how many times it goes, multiply that here, subtract it, and all that stuff, right? Okay, and if you've had Algebra 2, you've probably seen, but maybe not, how you divide one polynomial into another. Anybody seen that? That's something I'm finding, like on these assessment tests, people seem to be doing pretty well with that one. Okay? That's kind of good, because people don't do enough division algorithm with numbers because they get a calculator put in their hands too early. On the other hand, you can do too much of it, because once you've got it, you've kind of got it. Okay? But people need to use it every once in a while after 5th grade. Every month or so you should have some kind of a long division problem you do to keep yourself straight on it. It's a fundamental algorithm. You always know what you have to do next. There's no question about it. You just follow the procedure. That doesn't mean it's necessarily easy to figure out what number you get when you divide this into that. Well, that's number sense. And sometimes you make a wrong turn, but you know how to correct that. If the number's too big, you use a smaller one, right? Okay, so those are decisions that you make. So you have a step-by-step procedure that's guaranteed to work, right? So what's a step-by-step procedure here that's guaranteed to work? Okay, I'm going to give you one. It's not the most efficient, okay? But here it is. Okay. I'm going to say this. I'm just going to do it in terms of this problem instead of general, because I don't want to get too abstract on you, but it's easy to adapt. Okay, we subtract I want to use a symbol, though, instead of 37, okay? So we subtract 12 from x, okay? Because x is going to be this number. So actually I'm doing what I just said I wasn't going to do, but I'm kind of making decisions as I go here. So we're going to use x instead of 37, t for the 2 o'clock. Okay? So you subtract 12 from x. Okay? Now, okay, if 12 minus x is less than or equal to 0, then x becomes 12 minus x. Okay? So you replace x with 12 minus x. Make sense? Okay, so if we do that for 37,
What was that we used x to between the second x and 12?
I'm sorry, couldn't understand.
What was the symbol you used between the second x and 12?
Oh, you talking about this arrow here? That's an arrow pointing left. Should have made it look clear. I mean, it looks clear to me, but everything I write looks clear to me. Until I look at it again 2 days later and say, what the heck did I just write? Okay, so, yeah. Okay, everybody read this okay? So at this stage, okay, we start out, we subtract 12 from x. What do we get? If x is 37.
25.
I'm sorry?
25.
25, right? Okay. Okay. So now, what happens in this step? Well, is 12 minus x less than or equal to 0?
No.
And you know what I just wrote there makes no sense? I should have said greater than or equal to 0. Okay, so I'm glad I'm tracing this thing because I was a little careless there. Okay, so if x, 12 minus x is greater than or equal to 0, then we replace x with, and it's not 12 minus x. X minus 12. Okay? So again, being a little careless here. Okay, so now that I've got myself straight, I hope, what is the value of x going to be? What's going to happen in this step? First of all, and it's x minus 12. Actually, the way I wrote it first was right, but that was wrong. Okay. Okay. Is x minus 12 greater than or equal to 0?
Yes.
Well, if x is 37, x minus 12 is 25, and that's greater than or equal to 0. So what are we going to do?
37.
We're going to replace x with x minus 12, right?
Yeah.
So now what do we do?
You get 13.
Huh?
You get 13. You subtract 12 from 25.
Yeah, well, no. X is now what?
25.
Okay, you got to do that. X has to be 25. Okay?
Where did we get 25?
37 minus 12. X minus 12 is...
Oh, we're using.
Yes.
And there's something else I got to do here.
Yes, there's no...
I'll wake up soon.
You just gotta stop using things.
So I'm going to write it this way. Okay?
Here would the x be pointing the arrow to x minus 12.
Isn't that what you just wrote?
So, okay, so far we understand that if we start with 37, when we get here, this is going to be so now we're going to replace x with x minus 12, right?
Didn't we just write that
Isn't
way?
that what you just had?
That's
I'm
what-
sorry?
Isn't that what you just wrote, what you already had up there?
Yeah.
It is, but I've structured it a little differently. You'll see.
I'm confused.
Okay, if x, okay, otherwise, and I don't like the way this is developing, it's not elegant, but that's okay, because I want to show you an inelegant, less elegant algorithm than a more elegant algorithm, okay? Okay, so x is replaced by x minus 12, okay? I'm going to have to kind of use a go-to thing, which we don't really want to do, but that's okay. I'm going to say exit the if statement. This is a little closer to computer language than I want it to be. programming language, but it's okay. Okay? Be specific. Exit the if then else.
Exit.
You see what an if then else is, because I'm gonna write there's an if, there's a then, right?
What? Exit?
Huh?
What does exit mean?
What do you mean by exit?
You'll
Exit,
see.
quote unquote, if then else.
And, I don't really wanna use an if then, I wanna use a do while, but I'm gonna,
What?
That's what basically means. So, if this is the case, you do this. If it's not the case,
Oh, I understand. It went what I do.
Okay, my intention was to give you sort of a clumsy algorithm, and I'm doing a better job of it than I intended to. Okay, that's okay. Okay, so what's going to happen? X is now 37, right? Never mind. This is not, you know.
Are you doing okay today, Mr. Smith?
Huh?
Are you doing okay today?
Apparently not.
Do you want to use the
But we'll
police
get
hall?
we'll get there. I'm going to probably have to change this
Yeah.
because I'm writing nonsense.
Let's just give you some time.
So
Let's take a break.
Are you legitimately? Are you feeling okay today?
We
yeah,
can take
feel
our
pretty good.
few-minute break now.
Yeah, yeah. So just treat me gently. I'll get there. Okay. So I don't like any of that. So I'm going to do this. Again, I'm kind of doing this spontaneously, no excuse. Should have thought it through a little more before I started. So, okay, so. As long as x is greater than or equal to 0,
So we need to erase all of that again?
do the following. Replace x with x minus 12. Okay? Then and the as long as. Okay? And again, a little closer to computer language than I'd like, but okay. So, what do? You start with x, which is 37, right? Then what?
X minus 12.
Okay. You calculate x minus 12, and you know, there's still something, because we can end up with a negative x. Okay, so I'm going to replace this 0 with a 12. Okay, as long as x is greater than or equal to 12, we do this, because this is not going to terminate the way I want it to. Okay, so x is 37. What do? Is x greater than or equal to 12? Yeah, so you do this, right? And you get what? Now x is 25. Got it? Okay? Now, x is still 25, so we don't end, we keep doing what we do for the as long as until we meet this condition, right? As long as x is less than or equal to 12, we keep doing this. And once it is less than or equal to 12, well, we end this and go on to whatever's next. Okay? That make sense?
Yes.
Okay, so x is 37. What happens first time? You replace x with 25, right? Now, we do this again because x is still greater than or equal to 12, right? So now what's going to happen? X is going to become what?
13.
Well, x is 25. It's greater than or equal to 12. We're going to subtract 12. We're going to get 13, right? Now, is x still greater than or equal to 12? Okay, so we subtract 13 again. 12 again. X is 13. We subtract 12. We get 1. Now, is x greater than or equal to 12? No, it's 1. Okay, so now we do this and we get what? I'm sorry?
3.
We get 3, which is our answer. Okay? So, there's a problem with this because it doesn't always necessarily work, or does it? Maybe it always works. Is there any possible way that x here could end up either greater than 12 or less than 1? Because it's got to be between 1 and 12, right? Okay. Is there any possibility? Well, if x started out at 12, and you could check it number by number, okay? There are only 12 possible numbers, and that's, of course, sometimes you have infinite possible inputs to an algorithm, okay? But right now, there are only 12 possible inputs, okay? So you can check it out. If x is 1, will this thing terminate with a number that's between 1 and 12, okay? So I'm not going to get into all the detail of that, but I'll just say that t has to be at least 1, right? Because t is a reading on the clock that you start with. T is like this number. The smallest number you could have is 1. The biggest number you could have is 12, right? Okay, well, if t is 1, then x is going to be less than or equal to 12, right? No, x is going to be less than 12, because as long as x is greater than or equal to 12, so if x was equal to 12, you would still do this thing again, you'd end up with 0, right? Okay? And you'd add 0 to whatever t is, which will give you at least 1, because t has to be at least 1. Now, if x is 12, then, well, you're going to keep subtracting, well, until you get 0 here. So 0 is going to get added to this. And you're going to get a number here then that has to be between 0 and 11. So you're going to add a number between 0 and 11 to a number that's, what, between 1 and 12, right? Of course, now if you add a number between 0 and 11 to a number between 1 and 12, you can get a number bigger than 12, can't you?
Can we do some examples?
Well, we're doing one, but I'm going to ask you to trace it through. Okay, we'll take a few minutes to do that. So what I'm going to say now is that you also have to show Okay, so I'm gonna say it like this. Okay? That's an algorithm, we can prove that it works. Okay? Now, before we mess with this one, which we'll probably do a little bit later, I'm gonna give you a much simpler algorithm. Well, this one isn't bad. If you run through it for a few numbers, occupational hazard here. If you run through it, it'd be really funny if I had this thing set up as a chain reaction that went around the whole perimeter of the room and threw everything off the shelf. Okay?
Well, it might be
If
When
I
I
make
was in
a-
college, somebody did that to somebody's room. You don't remember, this is an engineering school. The guy opened his door and something fell off the shelf, which then triggered a chain reaction that threw all his books off his shelves, everything off the top of his desk.
What grade do we get if we do that to your room?
Yeah, well, you know, if you're good enough to do that, I'd probably give you
an A plus.
at least a
B
D
minus.
minus. Okay?
You say D or
And if you
E?
did it really well,
Okay.
the sky's the limit. You know, you might get a Nobel Prize out of this. Of course, you'd probably also get sued by the state of Virginia, or the Commonwealth of Virginia, for destruction of property. But I'd do my best to intervene for a light sentence. Okay.
For a what? So,
Okay.
so you don't?
Okay, I've got to find another place for this. I kind of like having it there, but it's kind of a hazard. Okay, so what do we do? Okay, here's another algorithm. Okay? Z equals x over 12. Okay, everybody know what that notation there means? You know?
Is it a floor function? Or a
Yeah, it's the floor function, exactly. Very good. And not everybody's gonna know that. All that means is, it's the biggest integer that's less than x over 12. Integer being like a whole number. And in this case, it'll be a whole number. Integer's not really a whole number, okay? It could be negative, and whole numbers aren't negative, but,
Instead of floor function.
okay? So you know what integers are. It's the greatest integer that's less than or equal to x over 12. So I'll make a little note here. The floor of any number, I don't want to use n because that's usually an integer, and I don't want to use x, z, or t because it's in the, so the floor of A is the greatest integer that's less than or equal to A. Now what do you get if you subtract the floor of a number from the number? Like if your number is 1.7, what's the floor? What's the greatest integer that's less than 1.7?
1.6.
1.699999999.
It's not an integer. What's an integer?
1.6.
Huh?
1.6.
1.6 isn't an integer.
1.7.
1.7 isn't an integer.
what would
One.
be?
1 is an integer
Why aren't decimals integers?
because that's not how integers are defined.
How are integers?
Okay, wait a minute now. We've got to stop and review the number system, which I asked you about and asked if you knew what rational numbers are and all that stuff, right?
Well, we did.
Now, you
but-
probably know about rational, irrational numbers if you used the quadratic formula or whatever, but maybe you don't know where these things start. Okay, and it's pretty simple, okay? you start with 1. And then you start counting. What comes after 1 if you're
2.
counting? 2.
3,
Yep.
4, 5.
Okay. Now, this goes on. I told you my 5.5-year-old grandson actually had the patience to count to 300. Okay? Which is the only real sign of aptitude we've seen out of him, but that's okay. No, he's a perfectly okay kid, but he's not doing anything exceptional. Yeah.
Not yet.
Yeah, we can hope. We're not worried about it. He's doing just fine. Bilingual.
Seriously?
How old is he?
5
Well,
years
he's
old?
his whole preschool, I mean, everything he's done since he was like a year and a half old, he's been gone to a bilingual, no, it's actually Spanish-speaking school that they pay some bucks to go to. They want to be bilingual.
Oh,
He is.
can't you do that? at
He
school?
probably swears at us in Spanish, and we don't know it because we don't know Spanish. Okay? Actually, in Texas, you learn a little Spanish. He's had Spanish babysitters, really, really good kids. So anyhow, that's beside the point. He has the patience to count to 300, which not every 5.5-year-old has.
Or you lose track the times you get to 300.
What?
Or you get to lose track the times you get to 300 when you count.
Say that slowly and clearly. I'm sorry.
When you count, you can lose track of counting when you're that young.
Yeah, well, I was counting with him.
Oh.
But every once in a while I'd be quiet and he'd say the right number. Okay. So, I mean, he knew after 299, I didn't say anything, he said, 300! Okay, you know, he knows the number system. That's not unusual. Lots and lots of 5.5-year-olds can do that. Most of them don't have the patience to count to 300. Okay? So that whole digression is just, okay, we know now how to count, right? Most of us are over 5.5 and we're smart and we know how to count. So those are the natural numbers. You ever heard that term before?
Mm-hmm.
Yeah.
Okay, those are the natural numbers. Now, what are the whole numbers?
All those in 0.
You get to use 0. Now, people got killed over 0. Look up the history of 0.
Huh?
Okay, people start saying, let's start using 0, and they say, you can't count nothing. Of course, they didn't have guns, you know, they used knives and swords and stuff, you know. Okay, this is, you know,
My gosh.
it was India, Middle East, you know, they had a lot of, and back in the, you know, I forget when, it was, I think before the year 1000, okay? That whole controversy came around. So people finally straightened that out and started accepting 0 after several generations, okay? And the church was big on, you know, persecuting people for talking about 0. Some places, not necessarily Christian churches, but Hindu, Buddhist, you know, Islam, and then Christianity was in there too. And I forget exactly how it all sorted out. But, you know, it's kind of the foundations of the universe. It's not the way we want to think about the universe. Yeah. So people finally started accepting 0. Okay? And then people said, well, what if you go below 0?
Negative.
Okay, I don't think there were any wars necessarily fought over that, but there was. It took a while to get that accepted. I'm sure some people got killed over it, but probably not to the extent they did over 0. Okay. So that gives you what, if you include the negative numbers? What do you call that?
Integers.
Those are the integers. Okay? So you start with the natural numbers that you can easily count with. You add 0 that you don't really use to count, but it becomes important, especially if you want to develop algebra or a complete system of arithmetic or placeholders. Okay? So you can learn that division algorithm. Okay? Then you include the negative numbers. Okay? And then you start including the imaginary numbers. Now, I could tell you a lot about why imaginary numbers are important, but they are. And then you can extend that to the quaternions, which turn out to be really useful. And then the octonions, which nobody really knows much about, but people are working on it because I think it might explain a lot of particle physics. Some people think it has promise. Everybody acknowledges that maybe it does. Some people think it's more likely than others. Okay? That's kind of the end of the thing because that's the last of a certain kind of field, a division field. Okay? Field over which you can really define division. There are only those. Okay, and that's way beyond, that's in deep abstract algebra. That's graduate level stuff. Okay? And my field was like complex numbers, functions of complex variables. So I find quaternions fairly easy to understand, but I don't go deep into them. And octonians, yeah, I get the idea, but I can't do anything with them. Except basic operations. I don't really know the field properties well. Okay, so those are number systems. Now, in this course, we're going to pretty much stick with real numbers, but sometimes complex numbers will come up. Okay? We're not going to do anything very deep with them, but they do come up. Like in the quadratic formula, you get complex numbers. You get complex number solutions. Okay, so that's number systems. So when I say integer, now you should know what I mean, right? So what's the greatest integer less than 1.7? It's not 1.6 because 1.6
Meg.
is not an integer. I could ask you what's the greatest rational number less than or equal to less than 1.7, but any rational number you think of less than 1.7, take a number halfway between that and 1.7, it's another rational number, right? So there's no rational number that's the greatest rational number less than 1.7. Okay? So 1.7 is kind of the ceiling of all those numbers, but it's not really a ceiling, it's a limit. Okay, well, you don't have to worry too much about that sort of thing, but it does sort of come up, so I mentioned it. So now when I say we subtract the floor of x over 12 from x over 12, what if x over 12 comes up 1.7? What do we get? What's the floor? Floor of 1.7 is
1.
1. Subtract that from 1.7, you get
0.7.
0.7. Okay? What's the floor of 48.92? So what do you get when you subtract the floor of 48.92 from 48.92? 0.92.
What do we do with the 0.92 after that?
That's z.
Huh.
Okay?
So subtract it, so 5.